Bohr model. Bohr model is the typical planetary model of the atom. You have a nucleus in there, which we'll talk about later. And then surrounding that nucleus are energy levels. You love chemistry. And the electrons reside on those energy levels. They must reside on one or another energy level. And they cannot reside between those energy levels. In fact, electrons would go from one energy level to another energy level without actually traveling the space between that. And if I could somehow teleport this from one to the other, I would do it. That would be a lot cooler. But they just jump. And they jump because they've gained energy. Now, in physics, we're going to take this look at it a little bit differently because we don't care about the fact that it's rings around the nucleus, not right now anyway. So we're going to look at it from kind of like a stepladder type of point of view. So a Bohr model of an atom would have several different energy levels. The lowest energy level here is going to be called the ground state. And there's a certain energy associated with that ground state. For hydrogen, it's something like negative 11.2 electron volts. That's the lowest energy that the electron can reside at. It's the first ring around the atom, if you'd like. And then each step up is associated with a different energy level. So this may be 6.4 energy level. Maybe this is a 2.8 energy level. And then there's a maybe 1.5 energy level. And then we have ionization. So if I have an electron that's residing down in the ground state, which it normally would, say this is a hydrogen atom, it's got one electron, and I give that electron, let's say 12 electron volts of energy, 12 electron volts of energy, it will ionize that atom, or ionize that electron. What does it mean to ionize? Add on or subtract. So the electron will leave the atom completely. It will take the first 11.2 and ionize.
Does that mean that it doesn't have an equal charge anymore?
Correct, because it would have a proton, and now it would not have an electron anymore. So it would be a positively charged hydrogen. So it will take the first 11.2 and ionize the electron. Well, what will happen to the other 0.8 electron volts? So I've given this electron 12 electrons of energy. The 11.2, the first 11.2, ionizes it. What happens to the rest of the 0.8? Disappear? No. No. It's taken as velocity. The rest gives that electron its speed as it goes away. So the electron is leaving with 0.8 electron volts, probably to another atom. It leaves with 0.8 electron volts of energy. And we can actually use that energy value to figure out how fast. Using what, do you think?
Kinematics.
I thought you were going to say it. Kinetic energy. Kinetic energy. I know how much energy it has. I know its mass, so I can figure out its velocity based on that. That's photoelectric effect, though. We're not quite there yet. For right now, we're going to get rid of this. And we're going to take our electron and put it back on the ground state. Now, the electron can only exist on these states, so it has to gain exactly the right amount of energy to jump from one state to another. Yes. There's actual numbers for the hydrogen. I forget what they...
But they're decided for each element.
Each element has a unique ladder of energies.
Is 11.2?
I think 11.2 is correct. Bohr model is like 11.2 EV times 1 over n squared or something like that. I can't remember exactly what the equation is.
Are there more levels the bigger it is?
The more electrons it has, the more Yes. The more levels it will have, the higher the ground state energy will be. Or, I guess, the lower the ground state. Yeah, something like neon, which would have, I forget how many electron levels on the Bohr model, like 6. Oh no, 2. Awesome. That was a good example. Maybe something like xenon, which has 5 electron levels, it would have many more available jumps to make.
And that just has to do, does that have to do with size, or?
It would have to do with size. And I don't know for sure, again, I would talk to our chemistry person first, but I believe the ground state would be at a larger energy. It would take more energy to ionize, say, xenon than it would hydrogen. It's a noble gas, for one thing. But yes, each element is going to have a unique set of levels. For the most part, I'm going to give those to you for any. But it's actually nice that each one does have a unique energy level set up, because we can then look at how the electrons jump and determine what the element is. That's what we would do in astronomy to determine what the sun's made out of. We can't exactly go to the sun and scoop up some material and bring it back to the lab and run tests on it. If you go at night, yeah. Certainly you could at night. Yes, at night. Oh my gosh. Brilliant. No. No, but what we do is we look at the electron transitions from the light that we're getting from it, and then we can determine what elements are there based on that. So the electron has to get a certain amount of energy in order to jump from electron level to electron level. How much energy would it need? 6.4 electron volt level.
Yes.
5.8. It would need 5.8 of absorbed energy. So this thing's at a low energy level. Energy comes in. Let's say it comes in and you get exactly 8 electron volts. And this thing will transition upwards. And it will sit. What do you mean? It's gained energy. It keeps it, but then it will fall down. Please. The electrons want, that was pathetic. The electrons want to be at the ground state. So what will happen, this is called an excited state right here. What will happen is it will spontaneously fall back down to the ground state. So when this electron comes from here and drops down to this ground state, what happens to the energy? It's released. In fact, it releases the exact same amount that it absorbed earlier. So what comes out of this is a release of energy, 5.8 electron volts, and that's released in the form of a photon. And this is light that we could potentially see if it's at the right energy level. Now, some of the energies are going to be released in the ultraviolet. Some of them may be in the infrared. Some of them may be X-rays or gamma rays or any other type of waves. But if it is released in our visible spectrum, then we could see it.